Here we go. So today we're going to start a new section. We're going to start section 4.3. We're skipping 4.2 for the moment. I'm going to come back to it a little later. But 4.3 is about maxima and minima, otherwise known as extreme values. Okay. So back in pre-calculus, you probably discussed briefly the difference between a local extreme versus a global extreme. Okay, or equivalently, relative extreme versus absolute extreme. These are two different ways to say the same thing. Okay, so if you have a function that goes like, and say it goes down, down like that, then we can identify points on the graph. This is a local maximum. I'm going to be using max and min to abbreviate maximum and minimum in this section and following sections. Here's a local minimum. Here is another local maximum. Okay, a local extreme just has to be bigger. It has to be a point on the function whose output value is bigger than the output values in the neighborhood of that point, right? So for values immediately to the left and the right, we can say yes. That is, this is the maximum value. If I zoom in, then it's the maximum value, right? If I zoom in on this, that point is the minimum value, right? If I zoom in on this, that point is the maximum value. But a global extreme needs to take into consideration the entire picture. Okay, so local is red, global is blue. Global is you look at the whole thing. Here's the question. Where is our global maximum? And do we even have one? Sure we do. This point right here. This point right here that I said was a local maximum is also a global maximum. Okay. It's the local max. It is a local max, but it is also the global max. How about global minimum? We have one local minimum. It's the only local minimum, but it's not the global minimum because at the height of that point, the height of that point is here, and there are other points down below it, right? And in fact, no matter how far down you go, you can always find more points, more function outputs that are even lower than that. So this graph has no global minimum. This function has no global minimum. So the global or absolute maximum and minimum are things that may or may not exist. Same with same actually with relative or local maximums and minimums. You might have a graph that has none of those. So like take, for example, the graph of 1 over x. Well, actually, okay, I guess I'm drawing negative 1 over x. This is y equals negative 1 over x. It doesn't matter. I could have drawn 1 over x, but this graph has no global extremes, neither minimum nor maximum, has none, has neither, but it also has no local extremes. So these don't necessarily have to happen, right? There doesn't necessarily have to be local or global extremes for a function in general. However, there is a theorem that says this: if f of x is continuous on a closed interval a to b, closed interval, okay, then f of x does have an absolute minimum and maximum on that interval a to b somewhere. This is called the extreme value theorem, I think. Just remember that. So yeah, it says if, and the key thing is here that the function is continuous and that the interval is closed. So I'm going to sort of highlight those in red here: continuous and the interval is closed. Then we're guaranteeing that it does have an absolute minimum and maximum. And if it has an absolute minimum and maximum, therefore it also has a local minimum or maximum, like by default, because anything which is a global or absolute max or min is also a local max or min, just sort of like I said, by default. That's actually not quite true. There's one silly exception to what I just said, but I'll leave it to you to see if you can figure out what it is. It's quite silly. It's not worth our time. But yeah, so the reason for this is because it's kind of obvious. It's like if you have a closed interval, then it's like you have a left boundary and you have a right boundary. It doesn't go off to infinity or anything like that. And you have a point on this side, you have a point, and you have a point on this side. Okay, so already there's a chance that one of these two might be the maximum or the minimum. And then what you're doing is you're connecting those dots with a continuous line. Like that, you know, somehow they're connected with a continuous graph, right? Now, it's guaranteed that there's gonna be a point somewhere on this graph, that somewhere on this portion of the graph, at least, that is the highest point on this portion, right? So if you're, so it's key to this is that we're talking about like just within this closed interval, there is a maximum and a minimum. So like, here's our max, right? Here's our min here. Yeah, that's guaranteed to happen. It might end up being one of the endpoints if it just goes down, right? If the graph just goes like this or whatever, then it could be that your max is over here and your min is over here. But it's guaranteed to have one. Okay, it's like guaranteed to exist. The reason that this graph doesn't, this example doesn't like contradict that theorem is because the domain is all real numbers, okay, which is not a closed interval. And it's not continuous because there is a vertical asymptote, right? There's this infinite discontinuity right here. We talked about discontinuities before back in chapter 2. So it's discontinuous, right? So so it breaks both of those rules. So it doesn't fall into it doesn't satisfy the conditions of that theorem. So it doesn't have to satisfy the conclusion either. So that's a little intro. Okay, sort of this stuff is sort of a little mostly review about local and absolute extremes, but also a little bit of new stuff with that new theorem there. Okay, let's move on to something a little more interesting. Oh, hang on. I just realized I don't have the chat open. All right, now I have the chat open. So I see no one has posted anything, but if you do post something, I'll be able to see you now. Okay. Right. So why do we want to know about extreme values? The answer is something called optimization. Okay. Optimization is a handy-dandy, useful thing. It is something that applied mathematicians or people who apply mathematics, like business people or engineers or statisticians or biologists or architects or physicists or computer programmers or computer scientists, at least, maybe computer programmers. Something that these people who apply mathematics often are wanting to know is the maximum or minimum value of something. How do you optimize? So for example, say you have a function, it's like a revenue function. And this is your production level. You have a function that goes something like, if you produce nothing, you make no revenue. If you produce too many things, you also make no revenue because you can't sell enough of them. Like demand isn't high enough. If you produce too much stuff, demand isn't high enough to sell all of it, and then your cost, well, and then like your revenue is, yeah, you can't sell it all. I guess it doesn't make sense necessarily. This is more of a profit. Let's talk about profit. If you produce nothing, you don't have any costs, but neither do you make any money. So it's like zero profit. If you produce too much, you have a lot of cost, but you can't make enough revenue to overcome that cost, so you make no profit. Somewhere in the middle is going to be max profit. Ching, 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 cha-ching. There's the dollars. That's what you want, right? Like, obviously, we want this from a business perspective. So if you can model this function, then figuring out where the maximum is a useful thing to be able to do. And so for some types of functions, it's obvious, but for other types of functions, it's not so obvious. And you need calculus to compute the location of that maximum or minimum directly. Okay. Now, there are numerical methods for doing this. I haven't talked to you guys much about numerical methods yet, but we are going to talk about that a little more at the end of this chapter. Numerical methods are like basically like, let's see if we can just guess and estimate. And often numerical methods are sort of like, let's do some sort of process and repeat it over and over again to get a good estimate. There are numerical methods for doing that as well. But what I'm going to teach you are the analytical methods for doing this, which are like the direct way to calculate the exact value of a maximum. Okay. So in order to be able to do this, we need another theorem. This is called Fermat's theorem. Fermat is a famous mathematician who had lots of different theorems. It's just one of them. For some reason, it's called Fermat's theorem. And here's the gist of it. That's not quite. Okay, if you have a function that's continuous, oops, easy. There you go, continuous function. Okay. The extreme values are going to occur at one of two sorts of places. Either they're going to occur at points where the tangent line is horizontal, so the derivative of the function will be 0. Okay, that's the case like there and there, for example. Or they're going to occur at a point like this one, a cusp or a corner, where f prime is undefined. And those are the only two things that can happen. So Fermat's theorem says this. If f of x has a extreme value, or just an extreme, okay, local extreme is what I better specify that. It doesn't have to be the absolute extreme, it just has to be a local extreme. If f of x has a local extreme at c, x equals c, like that's so let's say c is a specific value of x, okay? And if f prime of c exists, which is to say, you know, f is differentiable, there's that vocabulary, at x equals c, okay, then f prime of c will equal 0, guaranteed. That's the only way it can happen. It's the only way it can happen. It's got to be 0. Okay. So this means that if we want to find extreme values, one of the first things we want to do is take a derivative of the function and do two things. One, set it equal to 0 and solve for x, because you want to figure out where are those x values where the function equals 0. So f prime of x equals 0, and then solve. And actually, let's call them c. Okay. So that will find you some important points. Okay. And then you also want to figure out when f prime of x is undefined. That will find you perhaps some other points. But all of those points together are candidates for local extremes. So now we introduce a definition. We're going to define a word that will help us. A critical value or critical number of a function f of x is an x value c for which either f prime of c equals 0 or f prime of c is undefined. If you find all of the critical numbers for a function, then you have identified all of the locations where there could be local extremes for that function. Okay, and that's based on this theorem, this Fermat's theorem. Okay. Let's do a quick example. Hang on a second. So let's say you have the function f of x equals 2x cubed minus 9x squared minus 60x plus 28. Okay. Here's a function. It's a cubic function. We want to figure out where are the critical numbers. Let's find the critical numbers. To do this, we take a derivative. So I'm going to assume that we're mostly comfortable at this point with like the power rule. So I'm just going to go through this. It's a polynomial. So we just apply the sum and difference rules, the constant multiple rule, and the power rule. And we get the derivative of each term, right? So here we get 6x squared minus 9 plus 9, 9 times 2, 18x minus 60 plus 0. Right, the derivative of that 28 will be 0. So there's that. And then what we want to do is set that equal to 0. So f prime equals 0 and figure out where that could happen. 6x squared minus 18x minus 60 equals 0. Now I can factor out a 6 here. X squared minus 3x minus 10. Okay. How do I solve an equation like that? When does that equal 0?
The reason y is equal to 0 is Fermat theorem.
The reason we're setting it equal to 0 is because of Fermat's theorem, right? Fermat's theorem says that if you're looking for local extremes, then if the function's derivative exists, it's going to equal 0. The other possibility that's sort of maybe left unspoken by Fermat's theorem is that the derivative doesn't exist. That could happen too. So that's why we're going to end up looking for both of those things. So, but I'm starting with setting it equal to 0, okay? Because if the derivative exists at the local extreme value, it's going to be 0. So yeah, so this factors. Okay, so review factor.
X is x minus 5 and x plus 2.
Fantastic. X minus 5 and x plus 2. Good. So you'll be practicing your factoring skills this unit. Okay. And so then we have two solutions. We have x equals 5 and x equals -2 from that. So these are critical numbers. These are the critical numbers you obtain by setting the function equal to 0. But there may be other critical numbers. And then what's wrong here? I don't get it. All right, here we go. These might not be the only critical numbers. You also have to consider the other possibilities. Two possibilities. One, f prime equals 0, but 2, f prime is undefined. Okay. So we have two critical numbers, but we have to check to see if we have any more that come from this other possibility. These two cases, these are two things that can give us critical numbers. We have to check both of them. Now, in this function, though, in this function here, we actually are not going to have any undefined. We're not going to have any values where it's undefined because it's a polynomial. It's a quadratic polynomial. The domain is all real numbers. It doesn't have any undefined, no discontinuities. So I'm just going to write never. This is key, though. It is important, okay, that you do check this. You must check, must write something. Okay, so in your work, when you are doing a problem like this, when you're doing this step where you're finding critical numbers, you have to check both 1 and 2. Even if the function's never undefined, I need you to at least write down something like, I checked, this function is never undefined. You need to write something like that, because I need to know that you are aware that there could be critical numbers that come from that possibility as well. I'll show you examples where there are some. Okay, so don't worry, we'll get to that. Okay, so the only critical numbers we have for this function are these two. And if we check the graph of this function, if we go back, if we get into Desmos and graph this 2x cubed minus 9x squared, blah, blah, blah. Let's take a look at what we see. I'm going to scrunch my x-axis a little, or my y-axis down a little bit so we can see this a little better. Okay, so there we go. So there's our graph, and as you can see, it is a classic cubic polynomial shape with a local maximum at this point and a local minimum at that point. Okay. So those numbers, those x coordinates, -2 and 5, are the numbers that we computed by setting our derivative equal to 0 and solving the equation. Okay, so just showing you that's how that's what we have found here. Okay, and we can also see, if we graph f prime, for example, we can also see that f prime is crossing the x-axis, right? It's hitting 0 at those values. Which is something we learned about back in chapter 3. So here is a question from Tony in the chat. If there's no critical numbers, what that means? Okay, so if there's no here, maybe this is what you're asking. If you set it equal to 0 and there's no solutions, if the derivative never is equal to 0, that doesn't necessarily mean there's no critical numbers. There might be critical numbers that you get from checking to see where the function is undefined. I'll show you an example of what that looks like maybe in a moment. Okay, but if there are truly no critical numbers, like there's no place where it's 0 and there's no place where the function's undefined, those are no critical numbers, well, then what that means is that the function does not have any local extremes, because if it did, they would have to occur at critical numbers. That makes sense? We can look at an example of that. That's pretty easy to make an example of. Let me export this page and we'll make a new one. It just means, I wouldn't say undefined, but I would say there are no local extremes. That's a more clear way to communicate the result there. Yeah, so today is 3/3. It's my buddy Grant's birthday today. And also several other friends from school. When I was in school, March 3rd, there was like a ridiculous number of kids who had birthdays on March 3rd, including my friend group. Okay, so here's an example of a function. F of x equals 5x plus 7. What's f prime? F prime of x equals 5. When is f prime equal to 0? Never. It's equal to 5, not 0. It's always equal to 5. When is f prime undefined? Never. So, no critical numbers. So, no local extremes. And indeed, if you graph this function, it looks like that. You know, y equals 5x plus 7. Does it have any local extremes? No. It goes up forever, it goes down forever. There's no local extreme values. No absolute extreme values. It's just a line, right? So there's an example of what Tony's asking about, I do believe, when there's no critical numbers. Let's look at, so we started with sort of a medium example, which is like a cubic function that had 2 critical numbers. Then we went to like a basic example, which is like a linear function, no critical numbers. Let's look at a more complicated function that has like several critical numbers. Okay, so let's look at the function f of x equals x to the power 2/3 times x squared minus 4. Hang on a second. Let me just make sure that's not too hard. Oh. You guys can work on taking the derivative of that. I think that's I think it's going to be fine, but let me just check. Oh yeah, it's going to be totally fine. Okay. All right, well, let's take a derivative first of all. This is sort of a product of 2 functions situation. This is an f and a g, right? So what I think we're going to want to do here is do like a f prime times g, and then add an f times a g prime. So in other words, we're using the product rule. Okay. So let's see. The derivative of x to the power 2/3 is going to be like 2/3 times x to the power what? See, we take 2/3, we subtract 1. 2/3 minus 1 is negative 1/3. Negative 1/3. And then we have g. So then we have x squared minus 4. Plus the original f function, which is x to the 2/3, times the derivative of g. Now, the derivative of the x squared minus 4 is just 2x, like that. Okay, so what do we have? I'm going to write this out. This is 2x squared minus 4 over 3 times x to the 1/3. Oops. Okay, and then plus 2x to the power 5/3. If I do 2/3 plus 1, I get 5/3. So that's That's a way to write it if you want. If we wanted to get a common denominator, we could get a common denominator of 3x to the 1/3. Get a common denominator here. It might make it a little easier to look at. This then becomes what? If I multiply x to the 5/3 times x to the 1/3, 5/3 plus 1/3 is 6/3, which actually is just 2. So it's like 2 times x squared minus 4 plus 2 times 3, which is 6. And then the x to the 5/3 times the x to the 1/3 is just x squared. Okay. Oops. X squared. Let me stop. This is algebra. I know this is some tricky algebra. So let's check to make sure you're all doing okay. We doing okay? Any questions about what you're seeing? Product rule. Hopefully, I imagine the product rule is fairly familiar, right? You guys, we just got finished with chapter 3, so you guys have been studying this stuff lately. But then you know, doing this stuff, the 2 stays in the numerator, the 3 stays in the denominator. The negative power means it goes in the denominator, but the rest of this can stay in the numerator. So like maybe translating to this fraction format is a bit confusing. We're also doing stuff over here like adding things together. 2/3 plus 1 is like 2/3 plus 3/3, which is 5/3. That's where the 5/3 came from, if you were wondering. And then 5/3 plus 1/3 is 2. So 6/3 is 2. So that's why it's now just x squared down here. Okay. We can go a little further here. We can actually distribute this multiplication by 2 across here and get like 2x squared minus 8. So then we have 2x squared plus 6x squared. This actually is going to be 8x squared minus 8 over our 3x to the 1/3. And if you factor an 8 out, it's just 8 times x squared minus 1 over 3x to the 1/3. Okay, so our f prime has now been simplified to this format. This is our f prime of x. Okay. Remember how back in chapter 3, I told you we don't need to simplify or manipulate at all our derivative? I said, hey, once you get the derivative, you can stop. But I think what I said to you is in future, we're going to have good reason to simplify it. This is that future that I was telling you about. Okay, because what we want to do is look at this function, and I've put it into this format because I think once you get it in this format, it's much easier to say, when is this equal to 0 and when is this undefined? Okay, we can figure that out pretty easily based on what we're looking at here. So based on this, when is this function equal to 0? And when is it undefined? Tell me, folks. Tell me in the chat. Oh, Okay, Zaki's given us an answer. I want to comment on how you wrote that. I want to correct your notation. You don't want to put the 0 inside of the function. That's a different thing. Okay, it's not what we're doing here. If you put the 0, if you do f prime of 0, that's like 8 times 0 minus 1 over 3 times 0. That's undefined. Right? So like that's not the first line there. You don't want, that's not, it's like communicating the wrong idea with that notation you used. Okay. But your answers are more or less correct. You're missing one. There's one missing here somewhere. Here's how we can go about this. If it's a fraction, it's going to equal 0 when the numerator equals 0. So 8 times x squared minus 1 equals 0. We don't care about the 8. We can actually divide both sides by 8 and just get x squared minus 1 equals 0. X squared equals 1. What happens when you take the square root of both sides of an equation like x squared equals 1? If I square root both sides of this, square root, what is my next equation going to say? Review of pre-calculus, folks.
Be plus or minus 1.
You're kind of skipping a step. Yes, that's the end result, but what step are you skipping? This is the step that I think some people don't even teach this. When you take the square root of x squared, how does that simplify?
That would be x squared per half. Yes.
Yeah, well, that's another way to write it. That's not really what I'm asking, but that is another way to write it. The way we simplify this is the absolute value of x. So this is the absolute value of x equals 1, which then has two possibilities, x equals 1 or x equals negative 1. So this is what I think people tend to forget is that when you reduce the square root of a square, what you get is the absolute value. And the reason for that is because the way the square root function is defined is as a positive square root. It's called the principal root. So that's really where the plus or minus comes from. Anyway. Otherwise, I feel like the plus or minus feels like just this magic thing that comes out of nowhere. It's like sometimes when you're looking at a square root, it's positive, and sometimes when you're looking at a square root, it's both plus or minus. And I feel like it doesn't make sense. But if you incorporate, if you correctly interpret this as an absolute value of x, then it makes sense why it has these two solutions, plus or minus. And that does not contradict the rule that the square root function gives us positive outputs only. It doesn't contradict it. In fact, it reinforces it. So anyway, sorry, that's just a little tangent, a little tirade about how to teach square root functions in pre-calculus. So there we go. Anyway, we had two solutions there, plus or minus 1. And then when is it undefined? For figuring out when a function like this is undefined, when we have it in this form of a fraction, we can set the denominator equal to 0. When is 3x to the 1/3 going to equal 0? Well, when x equals 0, of course. So these are all 3 critical numbers. We have 3 critical numbers. Now, going back to the original function here, f of x was x to the 2/3 times x squared minus 4. if we look at our critical numbers, they are -1, 0, and 1 in order. All three are in the domain of F. Okay, so these, all three of these are possible local extremes. And if we look at the graph, which I'm holding off on teaching you exactly how to determine which critical numbers are local maximums and which critical numbers are local minimums, because that's a topic for the next section. But if we look at the graph of this function, here it is, okay, we could see it has minimum values at both x equals -1 and x equals +1, local minimums at those, and then a local maximum at that x value where the function's derivative was undefined at 0. That's where the local maximum occurs. Okay, so that is the end of that example. Now, we do have like a minute, and with that minute, I'm going to show you something. One more example. Let's take the function, the simple function x cubed. The derivative of this function is 3x squared. F prime equals 0 when x equals 0. F prime is never undefined. So critical number. X equals 0. Okay, but is x equals 0 a local minimum or a local maximum? If I graph x cubed, tell me, is that point, which is at 0, 0, is that point a local minimum or a local maximum? No. Correct. Is it a local minimum or a local maximum? No, it is not. It is neither. Correct. Neither min nor max. So here is the takeaway from that. In all caps, extreme values are always critical numbers. But critical numbers do not always correspond to extreme values. It's like it goes one way, but not the other. Where can I fit this? I should have put another carriage return in there. Okay. So, not all, and there's lots of reasons. You know, we could say, oh, f prime equal to 0, but not an extreme. Right? Here's an example. Boop, boop. F prime undefined, but not an extreme. Right? So extremes happen at critical numbers, but critical numbers are not always extremes. So that's why earlier what I said, I think, was you find the critical numbers, and those are candidates for local extremes, right? If the function has any local extremes, they will be among those candidates. You just have to do a little bit of sleuthing to figure out which ones are actually local extremes and what type of local extreme they are, a minimum or a maximum. Or if there's imposters among those candidates who are not actually local extremes, they just happen to satisfy the conditions for local extremes, but not, you know, yeah. So that's what we're going to study next time. We're going to figure out how to do that sleuthing. All right, y'all. Have a lovely day. Have a lovely weekend. And I'll see you on Monday.